So in this doodlecast, we're going to cover part of chapter 6. Specifically, we're going to look at the difference between sampling distributions versus standard normal distributions. And I think it's important to kind of reflect back on what a standard normal distribution is, which is specifically from chapter 5. So in a standard normal distribution, we are dealing with z-scores, but these z-scores are related to raw scores. So if you recall, we're looking at x values. So it's an entire distribution that is created with raw scores. We are going to kind of transition into what is called sampling distributions. And sampling distributions are used when we're dealing with inferential statistics and we're trying to get a sample to represent the larger population. Now, often we don't have large sample sizes and we don't have all of the population information often. So what we have to do is create a sample that is very representative of the population. And so when we get our sample statistics, we need to compare that to that population distribution to see how different it is or how similar it is. And we use sampling distributions to do this. So when we think of sampling distributions, instead of it being raw scores, we're now looking at z equaling a mean, so m. So because the sampling distribution is a distribution of all the possible sample means that could be attained from a specific sample size for a population. So then we can use this to calculate our statistics and then to compare our sample to the expected population. This is truly our theoretical distribution that we're comparing our sample raw scores to. And what we do is we create all the possible random samples and we get means for those and create that distribution. So that kind of introduces you to the difference. So with a sampling distribution, it is created completely of sample means, whereas a standard normal distribution, it is created with raw scores or x values, very specifically raw scores. So at this point, if you're thinking about, okay, where does this fall within our PowerPoint presentation, at this point we're basically up to slide 4 on the PowerPoint, and we're going to talk about how we select different types of samples, and that's an important concept with research. And so to be able to compare our sample to the population, we have to have a procedure to select that sample from the population, and we want to have equal probability. So we want to have a probability of selecting each participant, and we need to have that remain the same. So if you think about, okay, I have 3 people in our population, and I put all their names into a hat, and I say I want to sample 2 of the people. Well, I want that to be equal probability for all 3 of them. So there's a couple of different methods we would use. We could use sampling without replacement. So sampling without, that's the key, replacement. And the key to this is that probability will change. So if I have those 3 people in the population and I have 3 names on a piece of paper, it's folded, and I put all 3 of those names in a hat and I pull out one of them and I pull out Sarah. Well, I'm going to put Sarah aside. Sarah had a 1 in 3 probability of being chosen. But then the probabilities change because I'm not putting her back in. So the next person that I pull will actually have 1 out of 2 probability of being chosen. So that's a sampling without replacement. And this is the most common method used in behavioral research because when we're dealing with humans, we can't put a human back in and have them participate in 2 different groups. So if we're selecting to have participants participate either in a control group or the experimental group, we can't put them back in to our pool because we can't choose them again because they're already a participant of one group once they've been chosen. So sampling without replacement is the true way that we obtain our actual samples for the study. The other method is sampling with replacement, and that is where we will replace every single time. So the key to this is that probability will remain equal. So will be equal. So it's going to remain equal no matter how many times. So if the first person I pull is Sarah, I'm going to put Sarah back in, and no matter who I pull the next time, they have a 1 in 3 chance. And then I put that back in, and they have a 1 in 3 chance. This method is how we produce that sampling distribution that I was talking about that's theoretical, that we compare our actual sample to. So if I kind of this in another way, okay, I'm going to do my population in black, okay, and then I'm going to lay over the top of it in purple my sample. Well, the population distribution, because I often don't have the actual population, it is basically created. So I'm going to go like this. It's created by using sampling with replacement. Whereas my sample that I actually obtain and actually use in the study is actually, the sample is chosen using sampling without replacement. So because humans, like I said, can't participate in more than one group, so it limits us. But this theoretical distribution that we compare everything to is utilizing sampling with replacement. And so in actuality, that is called theoretical sampling. So when we look at sampling with replacement, I'm going to just put replace, that it equals what is known as theoretical sampling. So every person is going to get put back in no matter how many times you sample. So it's based off of what is your population size and how many samples are you going to be taking from that population. So if we have, let's say, a sample size of 2 that we want to take from a population of 3 people, then how we would obtain the number of samples that we're going to take of 2 would be using n to the lower n. So it would be 3 to the second power. So we would need 9 samples using theoretical sampling. So it's as simple as that. That theoretical sampling is using sampling with replacement. Now, another form of sampling is very specific to our actual research. Okay, in our actual research study, we're going to use sampling without replacement. So this is how we're obtaining the actual sample that we're going to utilize in the study. And this is actually known as experimental sampling. Because the probabilities will change as you remove people. So to determine how many samples of a specific size will be selected from a population, you have a little bit a different method of going about it. It's not as straightforward as it would be in theoretical sampling, because we basically have to account for the probability changing after you remove one, each time you remove one. So let's say we have the same information. We're going to take a sample of 2 from a population, I'm going to put a comma, of 3, okay? In this case, we're going to use this method, and it's kind of a tricky one. I'm going to write down the equation. Okay, now these exclamation points that you're seeing, I'll highlight, maybe not, actually, that came out really odd. Let's get rid of that. Okay, let's go back to, here we go. Ooh, nope. There, we'll try that. Okay, well that is an exclamation point. We're going to erase. Here we go. Okay, now we're good. So the exclamation point basically means times the number, the next number below. So I'll kind of write this out. So capital N is our population size, which is 3. So we're going to have 3, and the next number below is a 2. So we're going to times that 3 times 2. And then the next number below that is 1. And we won't use 0 because that'll cancel everything out. So 3 times 2 times 1. And then we do the same. So we're really lucky because N, exclamation point, N is 2. So we're just multiplying 2 times 1. So it's basically 2 times 1 to be able to kind of look at just this portion, but then we have to account for the n minus n, which is 3 minus 2, which is 1, right? So 2 times 1, which is 2, times 1, and then there's nothing else after because nothing is lower than 1. So we're basically doing 2 times 1 times 1 is what it is. So once we get our answer, we should be getting 3. So with experimental sampling, taking a sample size of 2 from a population of 3, we will need 3 samples of 2. So that kind of gets us through basically your PowerPoint slide number 8. It gives you the difference between theoretical sampling and experimental sampling. And remember, the theoretical sampling is how we create our sampling distribution of means. So what we do is we create an entire distribution that is all conducted with the means of all the possible random samples of a specific size. So as you can see, and I'll kind of jump forward to slide 11, you can see I give you basically an n equals 2 from the scores of 2, 4, 6, 8, which are population. These here are your population, okay? So if I was to take all the possible random samples of 2, I have to consider, like, what would it look like if I was using replacement? So the first thing I always do is I just look at what would happen if I chose 2 first. Okay, so here's 2 is my first choice, and then I put it back in the hat. I could choose it again. So I'm going to say, first, or let's do it as, possible samples. So we'll do samples. Okay, and I'm just going to focus on like choosing 2 first. Well, I could choose 2 the first time and then 2 the second time. But maybe I chose 2 the first time and 4 the second time. So there's my other sample of 2. Or it could have been 2 and 6, and then 2 and 8. So here's a sample here. This. Here's a sample. Here's a sample. And here's a sample. So there's 4 possible samples of 2 from a population size of 2. Well, that just accounts for if I chose 2 first. So that's why on your PowerPoint you'll notice that I have first choice, because I'm focusing on 2 as being my first choice. But what if my first choice is 4? I have to account for that. So it could be 4, and I could choose 4 again, right? 4 and 2, 4 and 6, etc., etc., etc. So I'm just going to kind of do this as first choice of 4. So this gives you just an idea of how the random sampling. So if we have 4 numbers in the population and we're taking a sample size of 2, it's, if you remember using random sampling with replacement, it's 4 to the second power. So we should have 16 samples of 2 when you're done. And if you'll notice on your PowerPoint, slide 11, you do have 16 samples of 2. Once we get all of our samples, we get means for those samples. So 2 plus 2 is 4, divided by 2 is 2. 2 plus 4 is 6, divided by 2 is 3. 2 plus 6 is 8, divided by 2 is 4. So these are means. Once you have all the possible samples and then you get all of their means, you ignore basically all of your original pairs and you just use your sample means to create your distribution. And that is how a sampling means distribution or sampling distribution, if they are used in consecutive, it doesn't matter, sampling means or sampling distribution, which is different than a standard normal distribution. The sampling distribution is going to just comprise of means. So if you look on slide 12 on the PowerPoint and give you an idea of what this looks like, we have, this graph where we have 4, 3, 2, 1, and 0. And then we have 1, 2, 3, 4, 5, 6, 7, 8. And if you'll notice, for the number 2, we have 1. For the number 3, we have 3. For the number 4, for the number 2, we do not have 3, we have 2. I jumped ahead. 2. But for number 4, we have 3. Then for number 5, we have 4, a frequency of 4. And then for 6, we go to 3 again. For 7, we go to 2. And for 8, we go to 1. If you look at that, even though like my drawing is not perfect, it piles up around a normal distribution. If you notice our sampling mean, M equals 5. If you look at our original scores from the population of 2, 4, 6, 8, if we were to add those up, we would have 20. So sum of x would equal 20. Our mean, if you divide 20 by 4, would be 5. These are equal. So our sampling means will pile up around where our population mean is. And that's how that distribution is made. So your sample mean will equal your population mean. And specifically, we really, researchers always try to get a larger sample size. We're not usually using sample sizes of 2, but even with a sample size of 2, you can see that this piles up around a normal distribution with a mean the same as the original population mean. So then now we have this great theoretical distribution that we can actually compare our sample statistics to and see how far it differs or how it differs. So the fact that the distribution of scores kind of approximates a normal distribution is based off of what's called the central limit theorem. Oops. Let me erase that so I can spell correctly. Central limit theorem. This is the concept, basically, that that as sample sizes increases, N increases, the distribution will approximate a normal distribution. There's kind of a magic number that researchers try to hit when we're getting a sample. We always try to get N of greater than 30, because we notice that as our sample size hits 30, that's when we really start seeing it approximating a normal distribution. Whether or not the population is normal, we can see that the distribution becomes, that theoretical distribution becomes normal at a sample size of 30. So that's kind of a magical number, but based upon the central limit theorem, we can see as sample size increases, the distribution will start approximating a normal distribution. And again, magic number is 30. When we're actually conducting a study, we try to hit that, that normal distribution with 30. So the last thing I'm going to cover is what is called the standard error of the mean. So when we're dealing with sampling distributions, and if we're trying to determine whether, how close our sample is to the population, we need to account for the fact that there's always going to be error. So remember, sampling error. It is the discrepancy between the population and the sample. And there's actually a distance between the two. And no matter how many times we take a sample from a population, it's never going to perfectly represent the population. So what we do is we have to account for the measurement, how far the sample mean deviates from the population mean. And that's very specifically our measure what we're measuring when we use the standard error of the mean. Now, this could be notation SEM, all capitals, or we could use our Greek sigma with a subtext of M. These are both notations for the standard error of the mean, and what this is a measure of the distance that the sample mean deviates from the population mean. So this is very specifically utilizing, and I'm just going to utilize the one method. There's two different methods, but very specifically, I usually give you standard deviation. You could be given variance, and in that case, you're just going to go variance over n and take the square root of the entire equation. But if you're given standard deviation instead of variance, you've already, remember, standard deviation is already the variance take with the square root of the variance. So it's not to be confused or interchanged. Those are two different things. So specifically, the population standard deviation divided by the square root of the sample size. This will measure the amount of error that we can see between the population and the sample. So let's say we have a population with a standard deviation of 5, okay? And we have we're going to take a sample of just, let's see, we're going to have a sample of 25 people, okay? So we have a small standard deviation of 5, but we're going to get a sample size of 25 people. So to find the standard error of the mean, I'm just going to plug this in. 5 divided by the square root of 25. Okay? So remember, when we take the square root of 25, it's going to be 5. So our standard error of the mean is 1. That means basically on average our sample mean will deviate from the population mean by about 1 point. So it's how far it will deviate from the population mean. So let's say the population mean is 70. That means our sample mean will more than likely be above it by 1 point or below it by 1 point. So it could be 71 or it could be 69 or somewhere within there. So it will deviate by 1 point. And that's how we obtain that standard error of the mean to measure the distance between the sample mean and the population mean. And this is useful because when we have that theoretical distribution, we need to know how far that distance is between the theoretical distribution, which is a representative of the population distribution, and our actual sample distribution. How much distance is there between the two? And then we can start using that to test hypotheses, which we will cover on Monday during lecture. I suggest you review the PowerPoints, review this Doodlecast, and then answer the quiz questions to obtain your active engagement hybrid points. Thank you.
Made with Doodlecast Pro.